Okay, so we're looking at question 5 in exercise 1C. A couple of interesting things to notice. I think 5A you should be fine with. I don't have a pen at the moment. Basically, any x values that I put into this function here, y equals log of x cubed, those x values are going to get cubed, and therefore the curve will increase a bit quicker, i.e. I can try and sort of give you a very rough sketch. That would be my log x. When I start putting fractions in, so there's 1, it will go through the same point, but then dilate upwards a bit. So this would be a log of x cubed. It's interesting because this function here, you should know, could be rewritten like this using log laws. Alright, so any value that's coming out of that log is then multiplied by 3, and then that explains why this curve would be giving out larger values at this point. I won't spend time doing full sketches of these, just want to remind you your calculator can do them. This x cubed, it's interesting to compare that to this x squared. There's similar things happening here, but in this one they want you to compare to 2 log x, and I've just shown you that they're the same thing, aren't they? If we compare y equals 2 log x versus y equals log x squared, well, couldn't I rewrite this one as being 2 log x? And yeah, we can using log laws, but we're kind of assuming all the way through here that x is greater than 0. If I just leave it like this, then technically I can now use negative x values. I can put negative x's in there, like a minus 10 or whatever. Then when it's squared, it'll become a positive number which is able to be logged. So the graph should actually reflect that, and I might just use Desmos to show that. Desmos, I was doing this earlier here. So you can see here y equals log of x squared also includes negative x values, right? As opposed to if I just use 2 log x, I can't have logs of negative numbers, and you will only have quadrant 1 and 4 showing. You can only put positive x values in there. So that does actually change the domain, which is quite interesting. You've got this mirror reflection here. You've got an axis of symmetry, I suppose, or axis of reflection about the y-axis. And if you were stating the domain, you would say, well, x can't equal 0, but it can equal everything else. The way to state the domain for that would be simply to say x is not equal to 0. Now, what else do they do? In that question, they do translate vertically as well. Which one do they translate? So they do take this one and raise it up 2. So it's this one here, isn't it? Plus 2, and that will lift the black curve up 2. As you would expect, you could find this x-intercept as you would normally do it. I could quickly show that. So that x-intercept is happening when y equals 0. Hence, if we're trying to find the x-intercept, we would have to say, when log of x squared plus 2 equals 0. So we'd say log of x squared equals minus 2. Then we'd raise both sides of that equation to make them powers of e, so we can get rid of this log. Say x squared is equaling 1 on e squared. Then we could say we need the square root plus or minus the square root of 1 on e squared, which is the same thing as the square root of 1 on the square root of e squared, which is just e. And just don't forget there's a plus minus anytime you have an unknown variable in your square rooting. So these points are coming out at 1 on e. So that one's kind of interesting. So let me just check those questions. I think there was another comment I wanted to make there. Where are we? Questions. Oh, this one here. Just before I do B, 5D, I won't comment on too much. You can see there's a horizontal translation 2 units to the right compared to this reference y equals log x. Y equals log x minus 2 moves 2 units to the right and 3 units down. You can find the x-intercepts using powers of e. This one here is kind of interesting. Y equals 1 log of 1 on x. As your x values are getting larger, this number that's been logged is obviously getting smaller. So as x increases, you'll be getting smaller and smaller and smaller. Another way to see this equation, hopefully you've already seen it. If we've got y equals log of 1 on x, y equals, then we have this, don't we? Right, x to the power minus 1. Then using log laws, I can pull the power out the front and multiply by that minus 1. And so now at this point you could see that when we compare these two curves, this second curve here, all of the y values that were positive will now be negative and vice versa, and we'll get this reflection. So we might graph that and have a quick look on Desmos. No, I don't need to do that, it's over here. Oh no, I do need to do that. So we've got y equals log x. We're comparing that to 1 on x. Don't need the plus 2. And you can see that reflection that's happening there. Yeah, I don't think I need to say too much more about that. I think it's easiest to explain like I did using log laws and rewriting this as y equals minus log of x. Okay, but it does make sense. I mean, when we get smaller than 1, say we put in a fractional value, we're doing 1 divided by some fraction, we're now getting larger numbers that we're logging, hence why these powers are now becoming positive. I always think of graphs of logs as graphs of powers. There's one final comment I wanted to make on this video, and it's that if you were asked to sketch in a test or an exam, which you know that you are sometimes, don't forget you have your calculator. So for example, I've typed in 2 log x squared plus 2. That was one of the questions. I know that they're going to sketch because these are highlighted. When I've graphed this, I've used Zoom Standard, which gives me plus or minus 10 in my x's, plus or minus y. In this instance, that was enough. I just wanted to comment on the fact that these are asymptotes and they're not showing very well. Hopefully you've seen this before. but if you haven't, your calculator does this. It's not very good at this. I think it calculates to a certain point and then just stops when the numbers get too small. So you need to draw this with an arrow. You need to show it coming down. These lines need to be coming down. They should have arrows on the end of them, right? So you should be putting arrows. You should be doing them on your axes as well, right? There should be arrows everywhere. The axes should be labeled, y and x. I should be labeling the functions. This is y of log x squared plus 2, for example. And I should be indicating that these functions don't just stop. They keep going, you know, theoretically they're going forever there, right? So even this way. So don't get into the Year 12 exam and risk losing a mark just because you didn't put an arrow on the end of a function, right? If they define a domain, if they say, we only want you to graph up to x equals 10, right, then stop the graph at 10. But otherwise, it's easy enough just to put some arrows on.